Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore conservation of momentum. Now conservation of momentum is one of those laws which is similar to conservation of energy. Basically it states what you start with is exactly what you finish with. So whenever we take a scenario like throwing a ball or shooting a bullet or giving someone a push, what tends to happen is there's an equal and opposite reaction which is occurring to you. So if we take a person shooting a bullet, we get an action and reaction. Now we call that reaction, obviously the action is the bullet firing out, the reaction is the recoil of the gun. If you throw a ball, and in this case we've got a lady who's got a heavy mass, she's throwing that ball. Well, she'll notice because she's on some rollers and we were trying to remove friction, we'll notice that she'll move backwards in the opposite direction. Her whole movement backwards will have exactly the same energy as the ball moving forwards. Now we know that the movement is mass times velocity, hence momentum. So just like conservation of energy, what we start with is what we finish with, conservation momentum works in exactly the same way because we've got motion, we've got energy which is imparted. You see these two people here on ice skates. We've removed the friction. As soon as one pushes on the other person is going to resist slightly. So they're going to have to put that force in so that we're going to get a change in momentum. Now remember, because we're dealing with vectors here, one's going to go in one direction, the other is going to go in the opposite direction. Because they're going in opposite directions, when we take the two momentum away, we will start with exactly what we finished with, which was zero. Okay, so as we stated, Newton's third law comes into action in this sort of area where we've got action and reaction. And because we're looking at this idea of movement, we can incorporate this momentum and we can look at it mathematically to work out exactly what happens when they come together or when they move apart. Now there are two main interactions that we're going to be exploring in this video. Those two situations are explosions and collisions. So basically an explosion, and I googled this and just came up with a definition, is where a single object separates into two or more fragments. Now in this case we're going to just look in 2 dimensions. It's actually in 1 dimension, it's just going to be moving out. However, in reality you can have an explosion of a bomb where it's actually going to go in a variety of directions. So we've got 3 dimensions. And if you look at any forensics who go in and look at the bomb squads go in and check what's happened with respect to an explosion. Doesn't have to necessarily be a bomb, but any form of explosion. They'll look at debris and the movement of that debris, and as a result be able to pinpoint and trace back as to what exactly caused the explosion, and then they can rule out whether it's been arson or it's been a bomb or whether it's just been an accident, etc., etc. But it's all down to the momentum and movement of the various particles, the mass, the velocity, where do you find them from a specific point, and they can trace it all back. With a lot of observation we can work it all out and say what's exactly happened. Now the word explode was first used to mean a burst with destructive force. Well, that sort of makes sense when you think of an explosion. You've got a huge amount of energy. There's going to be a force which is going to cause the velocity of the object, the actual substance which is exploding, to move outwards. So because we're getting a change in velocity, hence we're getting a change in momentum. So we go back to what we talked about earlier with respect to impulse. And we get this change in momentum requiring a force over time. So we're using a force to generate huge amounts of energy, which is going to generate momentum. Hence, momentum is used to calculate explosions and also collisions. So let's look at a little animation I put together. Here's a bomb. It's not doing anything. It's just sitting there. We're waiting for the explosion to happen. As soon as that explosion happens, what happens is the pieces then move apart. Now I've put in there center of mass, because the center of mass initially stayed in the center, as we know, and that is basically the epicenter. That's where the explosion starts. That's the point where you would expect the bomb to be placed within a room or what have you. And all the parts move away from that object. So they're getting gradually further away, but the center of mass always stays in the same point. Now, this is useful if we want to extend our understanding of momentum. Now, each piece will have a specific mass. In this case, I've made it very, very simple. They're equally sized, but they don't have to be. And it wouldn't just be one piece. There would be maybe hundreds of thousands of pieces depending on the size of the bomb. But you would look at each individual piece, work it out in a three-dimensional structure. Now, we know that each piece has been given its own velocity, so it will be moving out. And obviously, depending on the energy, the mass, they'll have specific velocities, which will cause it to move different directions. And then obviously by looking at the damage that they cause, you can then work out exactly what's going on. So it's a lot of time, painstaking observation which will occur, and that's why you don't get results from explosions for a long time as they go through and look at each individual piece, collect from the scene, and then pull it and piece it back together. So as I stated, prior to the bomb exploding, the momentum was 0. After the bomb explodes, the momentum must always be 0. Now you'll notice that the velocities are going in different directions because we're dealing with those two equal pieces. When we combine them back, the result is that they should come back to 0 because we've got two different directions. Because I've got two equal masses, the energy is the same, and if we say that the energy was uniform, the force on each piece was the same, the velocity is going to be the same. So I've got M1V1 going this way, M2 V2 going this way. When I pull them together, they're just going to be taken away from each other, so I get 0. And hence this is where the opposite directions come into account. Now, the second portion of this, as well as explosions, we've also got collisions. Now, there are two forms of collisions. We've got rebounds and we've got coupling. So first off, rebounds is obviously like you'll get in things like pool, gas molecules, etc., where things rebound off each other. Also, car crashes is a good way of looking at collisions and rebounds. You obviously have a car moving with a certain speed and another car moving with another speed. When they crash, they bounce off. And the police will look into this idea using the concept of conservation of momentum, and from that they can work out which way the object was traveling, how fast it was traveling, the mass, etc., etc. So when you get somebody who says, yes, I was going the speed limit, they can work out by the damage and where things end up exactly whether they were telling the truth or not. In this situation, let's work with some pool balls. Now here what I've got is two pool balls. I've got the cue ball, M1, and it's going to hit the yellow stripe ball, M2. Now the yellow stripe ball basically has got a velocity of 0, it's stationary, it's not going anywhere. The cue ball has got a velocity of V1. So the cue ball hits the yellow stripe ball. So what happens is, as we get collision, note there will be some energy loss through sound. Now, in this situation, let's keep it simple. Let's say that it's a nice, clean effect. Basically, we would call this an elastic collision. Elastic basically means that all the energy is passed to the two balls. There's nothing else coming off. An inelastic collision would be where some energy will be given off, and in reality this will be an inelastic because we're going to get sound, we're going to get friction off the base of the pool table. There'll also be some energy which will be lost through the Q-tip as well. But in this case we'll call it an elastic. All the energy is passed from one object, all the energy from before will equal the energy after, and it will all be put into the balls. So let's work on that scenario. So let's recap. We've got M1 hitting into M2 and they collide. So what happens? Well, they go off in different directions. M1's going to go one way, M2 is going to go the other. Now in this case, we're going to look at just one dimension, but they could go off in two dimensions, and then we'd have to use vector components, horizontal and vertical. Noting in those situations that the vertical components will all equal out, horizontal components will all equal out, vertical components will all equal out. So as a result, they will equal what we started with. Now, if we pull all this together, we get the idea that the momentum before must equal the momentum after. So you then get an algorithm that you can see down below in red, where we've got M1U1, which is the momentum before of M1, plus the momentum of the second one, m2u2, will also equal the momentum of m1, m1v1, and the momentum of m2, m2v2. And obviously the directions are going to be taken into account. So let's look at an example. So in this case, I've got a cart with a mass of 2 kilograms traveling at 6 meters per second, collides with another cart of mass 4 kilograms traveling in the same direction at 2 meters per second. So you can see there's the before collision. You've got the two carts. I've got 2 kilogram in blue and I've got the 0.4 kilogram in green. They're both going in the same direction with 6 meters per second and 2 meters per second. So then they collide to each other because obviously the blue one's going to catch the other one up, and it bounces off as shown in figure 8.12. Now the figure 8.12 is actually the diagram on the right hand side. So after impact, the 2 kilogram cart now travels at 3 meters per second in the same direction. So there's been a change in speed. Okay, if there's a change in speed, there's been a change in velocity. We've got to calculate what the velocity of the 0.4 kilogram is going to be after the collision. So remember, we're conserving energy, so we're conserving momentum. So whatever the momentum is at the beginning must be the momentum at the end. So let's have a look at how we solve this. Well, we know that m1u1 plus m2u2, the momentum before, equals m1v1 plus m2v2, the momentum after. So we substitute all the information in that we know. Well, we know the first cart, the blue cart, was 2 kilograms and 6 meters per second, and we know that the green cart was 0.4 kilograms going at 2 meters per second. So I can solve that together. I also know after the collision that the blue cart was going at 3 meters per second, still 2 kilograms, but we don't know the velocity of the second cart, the green cart, even though the mass is still 0.4. Now we're stating it hasn't lost any mass, none of the shopping came out of it. So what we can then do is rearrange it, and we end up, clicked off very quickly there, but V2 is going to be positive 17 meters per second. Now positive basically means we're going to be going to the right. Obviously if it was going negative, it would mean we would be going to the left. Okay, so I hope that makes sense. So as it states here, the positive sign indicates the trolley is moving in the same direction as before. So what happens with the second one, which is coupling? Well, coupling is where we get two objects which one hits into the other, and instead of bouncing off, what happens is they join together. So all you've got to take into account is the large mass has been included. For example, an arrow sticking into its target, or two cars colliding head-on and the bumpers actually stick together. Locomotives work, a locomotive going into a carriage. So let's look at an example in this situation. And what we've got here is a supermarket trolley loaded with shopping as a mass of 60 kilograms. So you can see that in blue. It rolls across the floor at 4 meters per second and collides with an empty trolley of mass 25 kilograms, which is stationary. It's stationary, so it's zero. They become fastened together and roll on as one. So you've got this image where you've got your cart, stationary, another cart coming together. It goes and then they move off, hopefully together. Well, they are going to be moving together. All the shopping stays in the same place. We've got to calculate the velocity of the two trolleys when they're locked together. Okay, so you can see down in the diagram below, I've tried to represent it. You can see the blue shopping cart, which is moving, and the stationary shopping cart in green. And then you can see they're combined together. That's why I put that little line between them at the bottom of the carts. So what happens? Well, momentum before equals momentum after. So I substitute in. So m1u1 plus m2u2 will equal m1 plus m2 times a constant velocity. Now, they're coupled, so I just add the two masses together. So basically I get 60 times 4 is m1u1. So that will be the momentum of the first cart plus 25 times 0. Now, that's obviously going to be 0 because the object is stationary. It's going to equal a combined effect, and we're going to treat the two trolleys as though it's one trolley. So we add the two masses together, 85 times V. So all I have to do now is rearrange it, and I end up that V equals 2.8 meters per second. And this is positive, which means it's going in the same direction again. Okay, so I hope that's explained conservation of momentum to you. I'm going to put up in this post a video showing this whole idea of conservation momentum using some some carts in the lab, and I hope you find that useful, and I look forward to you joining me again. Thanks for watching.